Hey everyone, I thought in this online extra whatever, I thought we might have a look at, well, I guess we will expand on what I mentioned in the lecture about homological algebra, and we will explore how we can interpret the second cohomology groups of group homology and Lie algebra homology. And learn what that says about the group or the Lie algebra we are looking at. And before we start, I guess we should familiarize ourselves with the concept of an extension. Let A and B be groups or Lie algebras an extension of B by A is a triple EIP, where E is also group or a Lie algebra, and I is a group homomorphism or a Lie algebra homomorphism from A to E, and P is a Lie algebra homomorphism from E to B, such that the sequence, well, the trivial group or the trivial Lie algebra to A via I to E and via P to B, and then again to the trivial is exact. In other words, an extension is a group or a Lie algebra such that A is a subgroup or sub-Lie algebra, and such that B is isomorphic to the quotient of E by A. The way I like to think about it is that an extension of B by A looks locally like a product of A and B, but not necessarily globally. And I guess one small lemma, or I guess proposition, is that there always exists such an extension, namely the trivial one. Namely the one where we take the product, if we're talking about groups, and then the map element of A is mapped to A, comma, the unit, and an element of the product is mapped to just B. This for groups. I guess this is already the proof. And for Lie algebras, we have the direct sum. Again, with A is mapped to A0 and AB is mapped to B. And now the question is, are there more such extensions? And the big theorem that we are going to prove now is that those extensions are precisely classified by the second cohomology group. So we're going to consider the case of groups first, and we're going to switch our notation a bit. Let G be a group, or I guess let G and M be groups, such that M is abelian, such that M is also a G module. So an abelian group with a G action that behaves nicely with the addition on the group. Then there's an isomorphism between the second group cohomology group of, I believe it was G semicolon M with extensions of G by M modulo isomorphism. And maybe at the beginning here I should have mentioned a morphism between extensions is a morphism between the E's. So F EIP to E prime I prime P prime is a group or Lie algebra homomorphism from E to E prime, such that when we write the two diagrams, so we have star goes to A, goes to E on one hand, and goes to E prime on the other hand, goes to B, goes to star again. And here we have our F, such that this commutes. And an isomorphism is then a morphism of extensions such that there is another morphism of extensions such that the compositions are just the identity. And in order to prove this, we are going to proceed in two steps. Step one is we are writing the cohomology group in a bit more manageable way. This one is to show that the second cohomology group is isomorphic to the set of functions from G squared to M, such that for all x, y, z and G, we have x acting on f of y and z minus f of x, y, z is equal to f of x and y minus f of x and y, z. All of this divided by the set of functions such that there is a map G from G to M such that f of x, y is equal to g of x plus x times g of y minus g of x and y. Sorry, g of x times y. And the second step will be to show that this monster over here is isomorphic to the extensions, or that this group over here classifies the extensions. And we're just going to construct the extensions. So, step one. And for this, we have a look at, well, how was group cohomology actually defined? We defined H2 of G semicolon M was X2 over the ring ZG of ZM. So the way that we compute this is that we find a projective resolution of ZG modules, P in this case, and then we apply the Hom to each of those elements of that projective resolution, and then we take the quotients for the cohomology groups. In this case, we choose the resolution where Pn is Z Gn plus 1. So this is just formal linear combinations with coefficients in Z of n plus 1 tuples of elements of G. Now you might ask, how is this a G module, or how does G act on this one? And if F is in Pn, G and G, sorry. If we have a general element of Pn, it looks like a linear combination, and then we just have H1 I dot H, let's say H0 until Hn I over some index, some finite index set. And if we act with the element G of the group on it, this is just defined to be just the coefficients unhindered. And we just multiply every element in that tuple by G. So in a way, these are homogeneous. Now this can be thought of analogous to homogeneous coordinates. And actually what we are going to do in the first step is just dehomogenizing it. Now what map do we have between those Pn? We have the map Dn from Pn plus 1 to Pn, which just maps a tuple x0 until xn plus 1 to some alternating sum. Where we just omit the ith entry. And well, now we apply Hom M to this complex here, or to this exact sequence, and then we get the complex 0 to, well, hom P naught M, hom of G modules, hom P1M, hom P2M, and so on. Where we have the map D0, D1, and so on. And what this map does is just dn of some homomorphism phi is just phi composed with dn downstairs. So in particular, dn phi evaluated at x0 dot 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 xn plus 1 is equal to an alternating sum of phi with those tuples inserted. And the case we're interested in, well, we are looking for the second cohomology group. And this one is the kernel of D2 divided by the image of D1. And now we're looking at what the kernel and the image look like. First, I guess we write down what D2 phi looks like. Well, phi is an element, is a homomorphism from P2 to M. So if we look at a basis representation, it basically takes 3 elements of the group. So D2 phi should take 4 elements of the group. So x0, x1, x2, x3. And what does it do? We just omit elements x2, x3, 0, 2, 3, plus 0, 1, 3, minus phi, x0, x1, x2. So now if phi lies in the kernel of D2, that just means that this expression up here should be equal to 0. And now we're going to plug in a very specific combination of elements, namely let x, y, z be in G. Then we always have 0 is equal to, okay, now we are going to apply this identity to, I guess, 1x, xy, xyz. So we get 0 is equal to phi of x, xy, xyz minus phi of 1 xy, xyz plus phi of 1 x, xyz minus phi of 1 x, xy. And now we see that these things here all have x in front. So since phi is a G morphism, this thing here is just equal to x times phi of 1 y yz. So now we are going to define our first isomorphism. I call it D because it's dehomogenization. Do not confuse this with any kind of differential or anything. H2GM to blah, 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 where we map this phi to, well, some map that takes 2 elements of G. So X and Y is mapped to phi of 1 X, Y. This is a map from G squared to M. And, well, I guess for well-definedness, we have to check 2 things. Firstly, that this function here satisfies the formula that we gave, or satisfies the condition we posed here, satisfies x, f, y, yz minus f of xy, xyz. No, that can't be true. Okay. Was again giving the wrong map. Doing it like that. Plus f of x, yz minus f of x, y. But if we write our identity here in terms of f, or in terms of this function here, then I guess if we can just rewrite this condition here. Sorry. Call this thing here small f. And then we have f of x times f of y z minus f of xyz. Well, what is it? X of phi of 1 y yz. Oh, look, that's exactly that expression we had here. And what's that equal to? Well, that's phi of 1 xy xyz. Oh, look, it's this one here. Okay, and similarly, that one is phi of 1 x xyz xy. This one is phi of 1 x xy. And we see that this is 0 exactly by what we have derived up here. And similarly, secondly, we have to show that if f is of the shape g of x plus x times g of y minus g of x times y for some map small g from capital G to M, then it comes, then phi lies in the image of D1. I guess since I eventually want this map to be injective, we in fact want this to be an equivalence. So if phi lies in the image of D1, then we can write phi is equal to D1 applied to some map psi. But what does this mean if we write it out? Well, this means that phi of x0, x1, x2 is equal to psi x1, x2 minus psi x0, x2 plus psi x0, x1. So that in a specific case, for example, phi 1x, xy, we have psi x and xy minus psi of 1xy plus psi of 1x. And well, again, we can use linearity here, pull out a common factor of x. Okay, and well, we see that this is equal to the dehomogenization of phi at x and y. And well, we see that this is of the shape x times some function evaluated at y minus that same function evaluated at x times y plus that same function evaluated at x. So this is equivalent to d phi being in the set of those f for which there exists g such that f of x and y is equal to xgy minus gxy plus gx. So that shows that our map is well defined and surjective and injective. And I guess for surjectivity, we have to essentially show that this thing up here is an equivalence, but I guess that is pretty obvious. Because again, any map that satisfies those conditions can be homogenized again, and then we get exactly a map that lies in the kernel of D2. So I guess that marks the end of part 1, or step 1. Now for step 2, we are again going to subdivide this again. A, as we construct a map. Maybe I should give those things here a name. We call this thing up here We call those the two co-cycles, and those the two co-boundaries, just for fun. And now we're going to construct a map from the two co-cycles to the extensions. Then we are going to show that sort of equivalence modulo co-boundaries translates into isomorphism, or I guess is equivalent to isomorphism. And for C, we show that every extension can be obtained this way. So I guess C is that this map here is surjective. And step B is essentially going to show that on one hand, this map from C2 to the extensions passes to the quotient of C2 by B2, that quotient up here. And it is also going to show that this map is injective, and then we have surjective, so that it is a bijection. So we are going to construct an extension given such a co-cycle. And now we're going to call it differently. We're going to call it omega, just for kicks. Let omega be a two co-cycle. Then we define co-cycle product G to be the set. Well, as a set, we're going to define it as the Cartesian product of G, but we give it a different multiplication. Namely, we multiply two tuples in following way. I wrote them with a tilde. So we are going to take the first entry of the first tuple and add to it, well, not the first entry of the second tuple, but we're going to let G act on that one. And then we add the co-cycle evaluated at G and G tilde. And then we just take G tilde as the second element of the tuple. Well, we want to show that this is a group. So we have to show a couple of things. We show associativity. This is going to be a bit ugly, but I think I'm going to skip a few steps. So we're looking at a product of three tuples that is associated this way. And when we expand it all, we get an expression that looks like this. We have M plus GM tilde plus G tilde M bar. Then we have a couple of co-cycles. We have omega G tilde G bar. And then we have G times omega G tilde G bar. And then we have G tilde G bar. And yeah, I think we already used, okay, maybe I should write one more step in between. We have m plus gm tilde plus omega g tilde plus g tilde m bar plus omega g bar g tilde. And basically using exactly the property that omega satisfies, we get that this is the same as m plus, then we can pull out a factor of g m tilde plus g tilde m bar plus omega g tilde g bar, closing brackets, plus omega g tilde g bar, comma g tilde g bar. And this is now, after a couple of steps, equal to the same product but associated the other way. So we can see that, yeah, the associativity of the product is essentially due to this weird looking condition on our co-cycle, this condition up here. Then we want to have a neutral element. And that one is given by minus omega 1, 1, and 1, whereby 1 I denote the neutral element of G. And I guess you should have to verify that if you multiply it on the left and on the right, that you get the same thing, but it essentially just works out. And we want to have inverses. And well, for the element mg, the inverse is minus G inverse m minus G inverse omega G inverse minus G inverse omega 1, 1 and G inverse. And this is again takes a bit of calculation to verify, but it is indeed an inverse. So we have a group, and well, in order to get an extension, we have to define I and P. So we have I from M to G, and how do we define that? M cross omega G, and we define it by just having small m mapping to minus omega 1, 1, sorry, just m1. This can easily be seen to be a group homomorphism. And similar, we have that product to G, and it just maps mg to G. Okay, also works. Now the second step is we want to show that isomorphism, or sorry, equality modulo co-boundaries is the same as, or induces isomorphism. So we have assume that M cross pi G is isomorphic to M cross omega G. And let's call that isomorphism psi. Then we have, by definition, our commutative diagram. G to 1 and M cross omega G to G to 1. And we have our psi here. And we want this to commute. This means two things. Firstly, those are the same. And secondly, those are the same. Let's also split up our map. Psi, we have psi of mg, well, is again a tuple. So we call it psi1 mg and psi2 mg, where this one lies in M, capital M, and this one lies in capital G. And now what do these equations tell us? Well, if we first inject from M into M cross G and then go to the other M cross G, that means that psi of M1 is equal to M1. And secondly, the second equation tells us that psi2 of mg is equal to G. And yeah, I guess the next challenge is to write the general psi mg in terms of psi m1. So note that psi mg, that psi m1 psi minus pi 1 1 comma g, that this is by definition psi of m minus pi 1 1 plus pi 1 g and g. And from the identity that pi satisfies, it can be shown that pi 1 1 is equal to pi 1 g. So that's just 0, and we have psi mg. So this means that psi mg can be written as psi m1 times psi of minus pi 1 1 and g. But, well, we know what psi of m1 looks like, namely just m1, and then we multiply it by, well, and psi, we can split it up into psi1 and psi2. So we have psi1 of minus pi 1 1 and g, and then we have g because of the second identity. And by just multiplying by just applying our multiplication formula, we find that this is that, although I believe there should be a G there. Oh, no, not a G, because it should be that one there. Okay. Yeah, and here we have omega 1, 1 again, because omega 1, 1 is equal to omega 1 G. And well, if we squint a bit, then this just looks like some function applied to G. So what we're going to call this function, well, let's just call it f of G, because we haven't used any of those letters enough, often enough. Okay, now we want to somehow compare omega and pi, or we want to get some sort of relation between them. So I suggest that we have a look at the multiplication formula, because they only show up there, and also because, well, we know phi is a group, psi is a group homomorphism. So of course we want psi mg times psi m bar g bar to be equal to psi of, well, what is this? M plus g times m bar plus pi of g bar, comma g bar. Well, on the other hand, we have an idea of what psi looks like. So we can just apply that formula there. And we get that this is equal to m plus gm bar plus pi g bar. So exactly that expression here. Plus f of g bar, the product. And then that thing there as the second. Now, on the other hand, we know that this thing equals, well, m plus f of g multiplied with m bar plus f of g bar, which, if you write it out, is m plus gm bar plus f of g plus g f of g bar plus omega g bar g bar. So those two expressions here have to be equal. Can look at a couple of common features. Okay, those two things are there. And well, the second entries also match up. So if we look at the rest, we find that pi g bar minus omega of g and g bar is equal to fg plus g times f of g prime minus f of g prime. And if we recall our definition for coboundaries, we see that, well, first thing times function applied to the second thing minus function applied to the product. Yeah. First thing times function applied to the second thing minus function applied to the product. Yeah, okay, so this thing is in B2. And I guess working backwards, you find that this is an equivalence. And now for C, we sort of would like to first have a look at how we can obtain our, or let's say this construction has really two inputs. It has as input the co-cycle and it has as input the G action. So how do we recover omega and the G action on M from this co-cycle product? And well, let's also make one small generalization, or one small, well, not generalization, one small assumption. Because if you look closely, you can just define f to be something constant. And we have some constant minus that same constant. So what we are left with is I don't know, because of what we are quotienting by, we can anyway assume that omega 1,1 is equal to 0. And this is going to be very useful because it simplifies a lot of formulas. In particular, yeah, it simplifies the inversion formula. So and the thing is, well, for the G action, we have to look at conjugation. So we look at yeah, what happens if we conjugate an element I of M with an object of the form 0G. And well, firstly, what is this inverse here? Well, we have, looking for the inverse formula, minus 1 inverse times M, okay. And those two expressions here cancel, I think. And lastly, we have the G inverse. So this one is just, sorry. Is this just 0G inverse? Or let's say minus G inverse omega G inverse. I think that is more the case. So this is Gm plus G, well, that thing cancels, minus omega G inverse Okay, I shouldn't skip too many steps when I've written things not very completely. So we have 0 plus g times m plus omega g1. Now this thing is equal to g times omega 1, which is equal to 0. And we have g, and we multiply this by that thing there. So we have gm minus g multiplied by g inverse omega g inverse. So this is omega g inverse. And then we have plus omega g inverse, because we always have to include the cocycle, and then we have 1. So those two terms cancel out, and we have gm 1. Or in other words, I of gm. So our g action is indeed realized by conjugation. And for the other thing, for the omega, we're just going to look at, again, elements of the form 0g, namely 0g times 0g bar is equal to, well, we have a whole bunch of zeros, and then we have omega g bar, g bar. So this means that 0g bar times 0g bar inverse is equal to omega g bar 1. So in particular, we have that the map G maps to our cocycle product, G maps to 0g, is not a group homomorphism. And our omega sort of measures how much it fails to be one, namely by having, so what do we call this map? We call it J, JG prime. This is not equal to G bar, but it is related to G bar, namely exactly by this cocycle. So equipped with this, let EIP be an extension of G by M. We want to show that E is isomorphic to some cocycle product of M and G. So we have the exact sequence 0 MEG, 1 MEG to 1 of I and P. And well, one property is that, at least in the category of sets or pointed sets or whatever, this exact sequence always splits, meaning that since our map P is surjective, it has a section. The section usually isn't a group homomorphism, but it is at least some map. Then exists a map J from G to E, such that P after J is the identity on G. And now we define omega of G and G bar to be, well, if we look at it, well, we can take J of G multiplied with J of G bar and then multiplied with J of G bar inverse. And well, if we apply P to it, P is a group homomorphism, so it distributes so we have P of J of G bar inverse. And well, by the section property, this is just G bar inverse, so this is 1. So this object here is an element of the kernel of P, but the kernel of P is the image of I. So there exists an object, I don't know, S in M, okay, let's call it M in M, such that PJG, JG prime, JG bar inverse is equal to I of M. And while using the axiom of choice, we can just define omega to be such a thing. Yeah, I guess the clue is that our map I is injective, so it is indeed a unique element. So then, without any problems, we can define omega of G and G bar just to be that M, that unique M that exists. Well, this makes omega into a map from G squared to M, and I guess if you really wanted to, you could show that it is indeed a cocycle, and that is a cocycle, and E is in fact isomorphic to M cocycle product G. And that was the proof. Okay, now for the similar theorem about Lie algebras. So now we have a representation, or I guess we have that G be a Lie algebra and M a G module. Then the second cohomology group M characterizes extensions of G by M. And again, we are going to write things in a bit more manageable shape. Oh, I guess first we have to construct our projective resolution. And in this case, we're going to use the Eilenberg-Moore complex, where basically Pn is the universal enveloping algebra tensor with the nth exterior power of G. This thing is a free UG module because, well, it's just UG tensor with a vector space. So we can just choose a basis of that vector space, and then we will have a UG basis of this module. And in particular, to describe the transition maps, I guess we just have to describe D2. And what does D2 do? It maps phi goes from UG tensor G wedge G to M, and then D phi, D2 phi takes 3 elements, or sorry, we're going to look at what it does with the basis elements. So it takes one tensor X wedge Y wedge Z, and this one is equal to phi of X tensor Y wedge Z minus phi of Y tensor H wedge X wedge Z plus phi Z tensor X wedge Y minus, and now we have a whole bunch of commutator, or a bunch of Lie brackets, X Y wedge Z minus phi of 1 tensor XZ wedge Y plus phi of 1 tensor YZ wedge X. I guess if you look closely, you can find some sort of the expression for the exterior differential from differential geometry in there. But okay. So we have phi lies in the kernel of D2 if and only if that whole expression is equal to 0. And well, I guess when we write this in a more manageable shape, we really mean that we first construct a map from, or a group homomorphism from H to MG2, and now we have maps F from G wedge G to M such that some identity is satisfied. And which identity is it? Well, it's exactly something that looks like this. X F Y wedge Z minus Y F X wedge Z plus Z F X wedge Y minus F the bracket of X and Y wedge Z I guess that should be a, sorry, plus minus. All divided by those functions that look like f of x wedge y is equal to g of the Lie bracket of x and y for some g from the Lie algebra G to M linear. And well, what does this map do? We send phi to the map from G wedge G to M that, well, maps x wedge y to phi of one tensor x wedge y. And well, using the linearity, you can quickly verify that that's indeed an isomorphism. Or I guess in this case, a linear map that is invertible. Now the central question is, in what way does this characterize extensions? Or I guess, how can we build extensions using such a thing? So and now we define the cocycle direct sum. So let omega be, and again, we're going to call this thing here C2 and this thing B2. And then we will define the direct sum of M and G to be, well, on the level of sets, it's just the Cartesian product. And, well, I guess this thing as vector spaces with a special Lie bracket. Namely, we have AX bracket with BY. And we define this to be the bracket of X and Y in the Lie algebra G. And then we add to that omega of X and Y. Could that be correct? Maybe. Okay, figured it out. We define our Lie bracket on this direct sum by taking, well, we again get a tuple. The M component is going to be omega x wedge y plus x acting on B minus y acting on A. And the G component is going to be just the Lie bracket of x and y in G. And well, if you want to verify the Jacobi identity, you are essentially going to end up using this behemoth of an equation. And well, anti-symmetry, I mean, omega is anti-symmetric by definition. The Lie bracket is anti-symmetric by definition. And this expression here was written exactly in a way that it would also be anti-symmetric. So works, I guess. And yeah, I guess again, you could ask yourself, how can we recover omega and the G action? And I guess this just works exactly like for the groups, or not exactly, but similarly to the groups. And similarly, for the group case, you can also prove that any extension can be written that way, and so on. So this was not a full-length lecture, but we showed a nice result. And yeah.